Okay, well, thank you everyone for joining. This is our last lecture, and tonight's actually an exciting topic. This is one of my favorite kind of subfields of reinforcement learning, so I'm excited to get a chance to talk about it. So tonight we're talking about reinforcement learning, and as I said in the first lecture, we could break down machine learning approaches into three general categories. So we've talked about supervised learning. Those were methods like regression and classification. And we talked about unsupervised learning, like clustering. But we haven't talked about number three, so that's what we're going to do tonight. And just so you know, if I refer to reinforcement learning as RL, those mean the same thing. And sometimes I'll just use that as shorthand. So one other thing to note is that tonight's lecture is going to be a little bit on the shorter side, so that if anybody wants to present their final project ideas, they can, or ask any questions about aspects of the final project that they might have. So moving on, tonight's lecture isn't going to have a lot of math in it because reinforcement learning is kind of a deep field and we don't necessarily have all the tools to discuss it, but I'll point you in a couple directions so that if you are interested and think this is interesting, that you can kind of follow up on your own and see if you think you've got the skills ready to go a little deeper. So RL is a subfield of machine learning in which we seek to build computer agents. We could think of these as software agents that take optimal actions within an environment with respect to some defined long-term reward. So there's three key terms here that I've highlighted. The goal is to build agents. Agents are things that make decisions or choose actions. An environment is kind of you could think of it as the task and all of the logic associated with that task that the agent wants to complete optimally. And the agent decides what's optimal based on a system of penalties and rewards. So here's how I've defined each one of these terms. An agent is one of the three major components of the reinforcement learning problem. And an agent observes the environment and attempts to choose an optimal action from an action space. This will make a little bit more sense in a minute when we look at an example. An environment defines the way in which actions impact the problem setting and updates the observable state from one time step to the next. So you can think of these problems that agents are trying to solve as ones in which they're discrete time steps. So the agent makes a decision, that decision impacts the environment, something happens, and then it gets to observe the environment again, and it then has the choice of what action to choose at the next time step. And then there's also a reward framework, which provides positive rewards when the agent achieves certain goals and possibly negative rewards when the agent makes what I'll call mistakes. In training an agent, we need it to make mistakes because we need it to explore all of the possible choices it can make at every time step. So let's look at an example. Many of you are, or most of you should be familiar with the game Tic-Tac-Toe, where one player is the O's, the other player is the X's, and you alternate taking turns. And the goal is to get 3 in a row, either horizontally, vertically, or diagonally. So in terms of reinforcement learning, the state is the current status of the environment. So in this game, that means the state would be the board and the position of all existing marks. So if the agent is the O's, and it's their turn now, they get to look at the board and try to figure out what move is best. For those of you who have played the game, it's probably quite clear that the agent should place another O in the far right column in the middle row to block X's from getting 3 in a row. But the agent doesn't really understand that from the start. All it knows is it's allowed to place its O's whenever it's its turn, and it will get rewarded when it wins, and it'll get penalized if it loses or ties. So since we want to incentivize winning, we'll give it negative rewards for losing or tying. So the action is the move in which the agent chooses. So if the agent were to essentially look at this board, it would have 3 options. That's what we'll call the action space. And so it could put an O in the top middle, the bottom middle, or the middle row right-hand column. So whatever space it chooses is its action. So how do we train an agent, or how does it learn? The agent learns by observing the environment thousands or millions or billions of times. And the agent attempts to learn what's called an optimal policy, or in English, what you could think of as the best move to take in each scenario, well, kind of a strategy. So the agent attempts to do this by computing a value function, which tells it how much it should expect in terms of future rewards if it's currently in a state S and takes action A, and then continues using its current strategy or policy. So learning is the attempt to find the best strategy. So if we go back to the previous slide, the state S is the board, so the locations of the O's and X's, and it tries to learn a value function, which tells it in this state, if I take each of these actions, which action is the best value. So what it should learn is that if it picks either the top middle or the bottom middle, it loses on the very next turn, at least to an experienced opponent. So those 2 moves in this state will have a negative reward. On the other hand, if it places an O in the right-hand column in the middle row, it learns that it's at least stayed alive to play another turn, even though it might not win. So the reward will actually be a little bit better. And that's what it's trying to learn, is how can it maximize its total rewards by making the appropriate or taking the appropriate action in each step or in each state. So why do we care? Well, there's a lot of reinforcement learning examples that are actually very, very timely. For example, self-driving cars. This is something we probably read about in the news very regularly. So at this point, we have the technology using convolutional neural networks, something that we've kind of talked about. Shraman discussed a little bit in the example that he built with iceberg detection. Cars can use a similar technology to see aspects of its environment. It can see the roads, the lanes, other cars, pedestrians, road signs, for example, speed limits and stop signs, maybe stoplights. And it can also use its route guidance features, so maps and GPS, things like that, to learn to control braking, acceleration, turning, and what choices it should make in terms of, what route to take. Reinforcement learning is one of the ways in which we can train self-driving cars to work, to avoid obstacles and get people to their location safely. Game bots are another very common example. As demonstrated a few slides back, we could build an agent to play any game in which we could write down the rules and logic. So tic-tac-toe is a really simple example, but there are more complicated games, including board games like checkers, chess, and Go. So I think I shared in the first lecture the video about AlphaGo, which is a bot that DeepMind trained to play the game of Go and actually beat some of the top ranked players in the world. But game bots have actually also learned to play really complicated computer games like Dota 2 and StarCraft. And you can also apply these to business activities. So for example, you could attempt to train an agent that would buy or sell stocks based on a variety of stock market indicators. You'd have to share it lots of historical data about when were optimal times to buy and sell. And it would learn essentially if you do it correctly and if the data supports it, how to achieve a profit by trading and buying and selling stocks. So one of the reasons that I think this is cool is because you can take it and apply it to a lot of real world problems. So there's a project that I'm building right now that's very personal to me. So I like to ride bikes and race in triathlons. And let's ask a question. What's the best strategy for riding a hilly course? Should I ride with consistent power for the whole race? Should I expend more energy when I'm going uphill and relax when I'm going downhill? What should be my strategy or policy? And this is a way that I could actually kind of solve this problem and maybe even increase my time or decrease my time in races. So if I want to use reinforcement learning to devise a strategy, the first thing I need to do is build a simulated environment. So this is something that I've actually already done. The environment contains all of the physics. So translate how much power is going into the pedals, and it turns that into acceleration and velocity. So this is a slightly more complicated environment than tic-tac-toe because you need to understand things like the rolling resistance. So the friction essentially that occurs between the bike and the road. You also need to understand wind resistance. And you need to understand some basic physics about how power converts into acceleration. And if you know a little bit of calculus, you can convert acceleration into velocity and figure out how long it'll take you to ride a course given a certain strategy. And the agent, once it's fully trained, should be able to tell you at each scenario, what is the best level of effort to maximize or to essentially minimize your time. There's other complicated parts about this environment because you need to model the rider's energy. So they don't have infinite energy. If I work really hard going up a hill, I'm probably going to need some time to recover. I'm not going to be able to just ride at 100% the whole time. So when should I maximize my effort and when should I take it easy? The environment also needs a model of the course profile. So for example, the hills and valleys, and maybe any sharp turns that I need to slow down for. And the agent would get a reward for finishing the course, and it would get penalized the longer it takes to complete. So it's incentivized to finish it as fast as possible. And the action or action space would be essentially how much effort should I put in at every given time step? So the agent will get an observation of the environment. For example, how much distance is left? What's the current velocity? What's the current slope of the road? Maybe it needs to know how many hills are left, how much elevation change is remaining. If we can combine all that information, the agent should be able to learn. Now, I had every intention of showing this tonight, but my agent's taking a little longer to train than I expected. So you'll have to give me a couple days, and I will post some results on the course homepage. But I thought it was a good thing to talk about anyways, even though I'm not quite finished, because this might give you some ideas for how you might apply something like this to a problem that's meaningful to you, or maybe something that helps the community and the environment, which, as I say that, is a good segue into discussing our final projects. So Shreyas, I've got a couple videos I want to show with regards to reinforcement learning, and then I will turn it over to you if that sounds good.
Thank you, Dr. Willard.
Yeah. So if, Shreyas, can you still see my screen? Should be a web browser now.
Yeah, I can see your screen, yeah.
Yep. So one of the, looks like I'm accidentally drawing all over my screen. All right. So if you're interested in getting started with reinforcement learning, I'd recommend taking a look at this website. It's gym.openai.com, and I can post that in the course website. But essentially, it tells us right here, GYM is a toolkit for developing and comparing reinforcement learning algorithms. So it has a library of test problems called environments, just like we talked about, that you can use to kind of test out your reinforcement learning algorithms, test out your skills. And it's a good way to learn a little bit about this before you try to take on a more complicated problem. So here's one of the problems. Essentially, there is a cart here, and on top of that cart is a pole which the agent is trying to balance. And it can do that by moving the cart left and right. So I try to play this video, but at first the agent's really bad. It doesn't know what to do, so the pole falls over almost right away. But after we've trained it for a little while, we should be able to notice here that the agent has learned. This video is quick, so I'll see if I can get it to no, it doesn't want to. I'll play it a few times, but you see that the agent has learned that it can balance the pole fairly well by moving the cart left and right. So this is just a simple example of how the reinforcement learning algorithms can be used. In a slightly more complicated example, as I mentioned earlier, OpenAI has trained reinforcement learning agents to play the game Dota 2. So I'm just going to try to show a quick video here. If it's not working great, let me know, and we can stop it a little bit early, and I'll just post it to the course homepage if it doesn't end up working.
OpenAI's goal is to build safe artificial general intelligence. We know that AI can be extremely beneficial to humanity, and it's going to require fundamental advances to see what it's really capable of. Dota is a great testbed for artificial intelligence. It's a very complicated game with a large competitive scene. And what this means is that you have to develop new techniques. You have to push forward the boundary of what's possible in order to get anywhere. For this project, we're building a Dota player. We're starting with a bot capable of beating top professional players at Dota 1v1. The rules of Dota are so complicated that if you just think really hard about how the game works and you try to write those rules down, you're not even going to be able to reach the performance of a reasonable player. So our bot is trained entirely through self-play. It starts out completely random with no knowledge of the world and simply plays against a copy of itself, which means it always has an evenly matched opponent. And it climbs this ladder of skill level until it's able to reach the performance of the best professional players in the world. The International is Dota's World Championships. 20,000 fans come from around the world to watch professionals compete for a $24 million prize pool. Over the course of the International, we tested our bot against a number of professional players. It turns out that our AI has learned really robust skills in the game that is actually really competitive with these pros. Many of the pros wanted to keep playing the bot and started talking about using it as part of their training routine.
My first impressions is it's pretty easy to get tilted from losing to like a bot. And I think the problem relies in people don't usually expect such a strong bot. Now he has a double wave and I can't trade hits with him. And he's going to be level 3 before me with full HP. I think, I don't know, watching the replay, honestly, I just learned something. So it's pretty helpful. Like, I felt like I'm one of the strongest SFs, and knowing that this move, like if I can foresee that if I make this move, this will happen to my wave and this is what's going to happen. It's just pretty nice to experience it. Like, someone could tell me this could happen, but I think experiencing it is just another level of knowledge.
In addition to the pros, we thought it was pretty cool that a number of amateur players enjoyed playing the bot as well.
It does kind of, I think that it would open up out of the box thinking, because there's many ways to win a game of Dota specifically. Okay, he's ignoring the fairy fires. The bot is good. The bot is better than I could have ever imagined. That we can get one hit from the donkey. Hello. He took the bait. Okay. So, your bot does not attack random things on the ground.
Does not attack random things on the ground.
It predicts where you go in the darkness. Yeah, that I did. Can I play again?
You're very welcome.
Okay, we're gonna go one more.
This event was us introducing our Dota project to the world. The next step is to try to build a team of 5 AIs and see if we can get it to reach the level of the top human professionals. Beyond that, we want to start mixing together AIs and human players on a single team and try to reach levels of performance that neither of them can reach on their own. We're super excited to see where that goes and hope that you'll stay tuned.
So as you can see, it's a pretty amazing technology that can be used in a lot of different ways. I want to show one more video, which I think is even more fun. In this video, OpenAI trained multiple agents to play hide and seek. So there were 2-person teams, 2 on each team, and they could use different aspects of their environment to hide. And so the blue guys that you see here were trying to hide, and they could move around blocks in order to try to prevent the red team from finding them. And I find it quite amazing, some of the strategies that they've learned. So let's watch this video as well.
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observe, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide and seek in parallel for many days. They train against each other as well as past versions of themselves using an algorithm called self-play. Coevolution and competition on Earth led to the only generally intelligent species known to date, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior from multi-agent interaction. We hope that with a much larger and more diverse environment, truly complex and intelligent agents will one day emerge.
Okay, so I thought that was really cool because these AI agents, these reinforcement learning agents, have learned to work together, even though they've never actually been explicitly told that they can work together or should work together. And they've picked up techniques. If we scroll down here, we can see that, you know, they've learned to move boxes into these gaps in the walls. Again, this is something that they were never told that they could do. It's something they figured out that they could do based on millions of games of hide and seek in which they probably always lost until they figured that out, that they could move these boxes and that would prevent them from being caught. As you can see, initially the seekers, the red team, had no problem finding the blue team. And then all of a sudden, they were forced to come up with a new strategy, which they did. They were figured out that they could use ramps to get over walls or over obstacles. So here we are. And then we move on a little bit further and the hiders learn that they can just steal the ramps. And then finally at the end, which I think is quite amazing, the seekers have, what we'd almost think kind of cheated. They did something that the creators never thought they could do, which was to get on top of the boxes and somehow move them around and allow them to get over walls. So it's pretty impressive what they were able to do. Now, something this complicated requires a lot of computational power, but it shows the amazing potential that reinforcement learning has in the machine learning world and kind of, you know, for things like self-driving cars and many other applications in business. So feel free to kind of expand your concepts of what you might think about for the final project to include reinforcement learning. You definitely don't have to, but this is a very cool technique that is very powerful and actually a lot of fun to watch. So with that, I'm going to hand things over to Shreyas, who's going to talk a little bit about the final project and some other things.
All right, thank you, Dr. Willard. That was a great lecture on reinforcement learning. So I would like to thank everyone for their time and effort that you guys put into this camp. I would especially like to thank Dr. Willard for his time, dedication, and hard work to make this camp a success. Thank you so much, Dr. Willard.
You're very welcome.
Okay, thank you. So we hope that all of you guys enjoyed it as much as we did. And we'll keep you guys notified as we keep conducting other AI events, so maybe similar camps and things like that. So now I would like to talk to you guys a little bit about the final project. So the final project is going to be due on the 18th of August. And this is a very good assignment to help you synthesize content and to see how you can actually use what you have learned in this course to actually develop a real world application. So you can use anything that you have learned from week 1 all the way up until this week where we learned about reinforcement learning. And while actually developing the application is not actually required for this assignment, we really encourage you to build the project after the camp. And by the 25th of August, we'll finish the evaluations of the final project, and we'll post the top 10 winners and send them medals by post. And we'll also send the course completion certificates through email. So on a related note, Dr. Fairchild from the Los Alamos National Laboratory will be presenting a talk on using AI and data science to actually tackle COVID-19. And this will be a very informative talk, and I encourage all of you guys to join it. And we have the registration link. We have the registration link for that in the chat here. So Strawman, would you please post the link?
Yes.
Okay. All right. Thank you. Yeah. And for manual students, we just launched our AI Club website, and I'll post a URL in the chat. Please look over it. And if you would like to join, please fill out the registration link on the website. And for those of you who don't attend manual, we highly encourage you to start a club at your school or your community so you can share what you have learned to your peers. And we can also help you achieve this from creating club materials to giving advice. So if you're interested in starting a club, please fill out the partner sign-up form on the website. And before we move on to questions, I would really appreciate it if you would turn on your camera so we can take a group picture. This is our last lecture. One second, everyone.
And just to elaborate on one thing that Shreya said, if you do want to work a little further on your final project and actually want to implement it, feel free to send us a note and register to get involved, and it's something we'd love to work with you on. All right, Shreyas, are you planning on taking the picture?
Yep. Yeah, we're done. Yeah.
Oh, we've already taken it?
Yep.
All right. I think some of us forgot to smile, but that's okay. I'd also like to ask that everyone, I appreciate all your time coming to these lectures. This is the first time we've tried to do this. And as far as I know, this is the first time that anyone's tried to really teach a course on AI and machine learning targeted to students in middle school and high school. So please give us some feedback. What did you like about the course? What didn't you like? What was maybe too difficult or what was too easy? Be nice to us because this is obviously our first time trying this. But we'd love to get feedback so that we can do this again better. And also feel free to comment on things that you'd like to learn about if we were to do a round 2 or a intermediate level course. We're open to lots of suggestions because as Shreyas has kind of pointed out, this is a very new organization and we're definitely looking to grow it and make it better.
Could everyone again turn on their cameras, and this time can everyone smile?
You should probably give us a countdown.
Okay. Yeah, this is good. I guess, yeah, this is good. Yeah, and people can turn off their cameras now. They want.
All right, thank you. Sharice, did you have any more material that you wanted to discuss?
Nothing else.
Okay.
Yeah, so we can now go on to questions.
It looked like there was one question earlier about what kind of physics engine did I use. I actually built my own, since this is kind of a simple application, simple relative to, you know, maybe games that have much more complicated physics in which you're interacting with lots of different objects. It's really just trying to learn about you know, how power impacts speed relative to the grade of the road and rolling resistance and aerodynamics, and then the energy model. So there are physics engines that you can use, and you can actually tie a lot of those into the GIM kind of framework that's built by OpenAI. So I encourage you to read more about that if that's something that you are generally interested in. We have a question that's, is it okay if we start creating our idea for the final project? Yes, and you can also take this time if you have questions about the final project or want to run ideas past us, feel free. That's, you know, what we're here for. So we'll take questions on the final project or on tonight's lecture. All right, it's very quiet. We'll give you one more minute. If there's no questions, we'll call this lecture over early. And we look forward to hearing we look forward to hearing all your final projects.
Yeah, you can present if you want to. Yeah.
Hi.
Hello. Yeah.
Yeah. So my project would be identification of the strain of COVID-19 using multi-label classification, artificial neural networks, and categorical transformation. The user will be asked a few questions which should be answered in yes or no. For example, do you have fever? Then the input will be converted using categorical transformation, and a neural network will classify it into the applicable classes. And this process will be repeated until all the symptoms are assigned to one unique class. This software can be used by government agencies, public healthcare units, and research centers. Yeah.
That's a fantastic idea. I'm not a biologist or a medical professional, so I don't know how closely the symptoms are tied to the individual strains of the virus. Do you know if there's a relationship between the strains?
Yeah,
and the
like
symptoms?
some research centers are actually investigating that. So some results and analysis have been found already. So I'll be using all that information to build my model.
Okay, great. I think that's a wonderful idea.
Yeah, I really like it as well.
Okay.
Yeah.
Hello. Okay.
Okay.
Yeah. My name's Shashank. My pitch was, so this project's aim is to make an artificial neural network model that can find the location of an exoplanet only by observing the exoplanet's gravitational effect on nearby planets and stars. NASA's probes generate about 12 terabytes of data every day, all of which have to be processed. In those 12 terabytes of data, there are signs of worlds beyond our solar system, worlds orbiting other stars, and worlds that may contain other life forms. As sensors and tech progresses, more data is generated, and machine learning can be applied to more efficiently sift through the data and help find new worlds.
That's very cool. Have you, do you have any examples of this type of data? So I know you said it comes from NASA.
Yeah.
Is it gravitational readings? What format is the data in?
So for the like little research that we did, we found a lot regarding like the distance between different stars, and also we took like JSON files, which were like pixels of like readings from different satellites, and used those to classify different exoplanets.
Very cool.
A good idea.
Dr. Willard,
Yes.
I haven't created a pitch yet, but like I plan on like creating a general idea for my project pretty soon. So is it okay if I can email you or Shreyas about it?
Yeah. Why don't you just send us a private message in the Google Classroom? That should be fine.
Okay, cool. Thank you.
Okay, hi, I'm Sanria and I'm working with DVJA. And so basically for our project, we all know that coal is the main resource that we use to generate electricity. But the problem with coal is that it's non-renewable, so eventually we're gonna run out. However, trash, we sure do have an abundance of that as it's polluting oceans and the land. So if we were to burn trash to create steam to power turbines, to generate electricity instead of using coal, that would be very beneficial to the environment. And now my partner Divija will explain where AI falls into this.
Thank you, Sanria. The AI will use classification and supervised learning connected to a computer program in the form of a camera to oversee the trash. Whereas a human might not be able to clearly distinguish if the trash is combustible or not. Therefore, the AI makes the job easier and well done. Yeah.
It sounds very interesting. So the goal of it is to find combustible trash. Can we also look for trash that would have non-harmful byproducts when it's burned? Because I know like things like plastic might be able to burn, but it might also create a lot of additional pollution.
That's what I said, but like when I was talking about it with Sanria. But I think, but like since it's like a 30-second pitch, we'll like go more into it in that final project. So.
But if we were to consider it, there are actual like electricity like plants in Sweden that work like this, like with a little research, and they use filters on their like exhausts to try and prevent harmful toxins going into the atmosphere. So
great, very cool.
Does anyone else have a pitch?
Shreyas?
Yes.
So in our final project, do we have to explain like how we're gonna find the data, or can we just say that we'll be using like a like fabricated data?
Well, it's not a requirement to say where exactly you'll get the data from, although if you want to, you can include it.
Okay.
So it's a good thing to think about just in general. That's one of the major problems that prohibits some people from being able to actually execute projects is not having the data available. So, you know, it's not a requirement, obviously, that you complete these projects, but it's good to think about, you know, would you be able to get the data? And does the data already exist? Or might you have to start collecting it or work with someone else to collect it? You know, for a lot of us, for example, we don't have satellites orbiting the Earth. So if NASA isn't there to provide us data, we wouldn't really be able to look for exoplanets. So, you know, it's good to think about what's the data availability and, you know, what can we do if it's not available? Is there any chance to get it? So Rishi, I think the way they plan to use AI was to use video analysis, computer vision to detect which pieces of trash are actually fit for burning. Would anyone else like to share? Or do we have any final questions? Yes, you're still welcome to work on your pitch. But I think at this point, since there's not many more questions, we'll probably end tonight's lecture. And if you want to run things by us before turning in the final project, feel free to contact us on the course webpage. Shreyas or Shraman, do you have anything else tonight?
I have nothing else.
Nothing else, yeah.
Okay. Well, thank you, everyone. I appreciate all of your attendance. We've had a lot of fun doing this. So really glad that everyone joined. And as I mentioned before, please send us feedback. And if there's more things you want to learn about, let us know. And we might think about putting together some more lectures, maybe either in the fall or over the winter. So again, thank you.
And thank you, everyone.
Thanks.
Bye.